Hi, I'm Bryce Sandlin from the University of Waterloo, and our talk is a simple algorithm for minimum cuts in near linear time. This is joint work with Nalan Barwaj from the University of California, San Diego, and Antonio Molina Lovett from Princeton University. Okay, so most of you probably already know, but what is the weighted minimum cut problem? Well, it's given a graph G on a vertex set V. We want to determine a non-empty vertex subset S such that the total weight of edges from S to V minus S is minimized. So I have just a little example here, and the minimum cut in this graph is right here, separating these two vertices from these three. So what is the weight of the minimum cut? It's the total weight of the edges crossing the cut. So here, the example, it's 10. Okay, so the minimum cut problem has a rich history. Most of you probably don't know all about, so I'll try to briefly cover these different publications. Okay, so the first solutions to the minimum cut problem were based on network flow. The minimum cut problem was assumed to be harder than network flow. And so the first solution was to just compute O of n squared network flows. And then this was improved by the Goldmurray-Hu tree, which can compute all pairwise flows with a linear number of flows. And finally, this flow research for minimum cuts concluded by this paper by Howe and Orlin, which showed that you can compute a minimum cut in complexity within a constant factor of that you can use to compute a ST max flow. All right, so this algorithm is based on, this talk is based on simple minimum cuts. We should think of other simple minimum cut algorithms, and one of which is the Stillwater-Wagner algorithm. And this algorithm computes an arbitrary min-ST cut, contracts the vertices S and T, and repeats. And by computing this arbitrary min-ST cut rather than a specific one, you could do so a little faster. And you get complexity nm plus n squared log n, the Fibonacci heap, or nm log n with a binary heap. Okay, so there are a couple algorithms based on edge contraction, and this first one is commonly referred to as Carter's algorithm. We're going to refer to it as Carter's randomized contraction algorithm since there are several results by Carter. And this algorithm is just pick a random edge and contract it, and you repeat it until there's only two vertices remaining. And there's a 1 in theta n squared chance that you found the right minimum cut. And you can just repeat the algorithm n squared times with an extra log n iterations to get to high probability, and then you find the minimum cut with probability 1 minus 1 over a polynomial in n. Okay, and this algorithm was improved by Carter and Stein in '96, and basically the idea is that the probability of contracting the minimum cut is higher towards the end of the algorithm, so we can actually just branch the algorithm and we spend more time at the later iterations. This actually ends up producing about a factor of m. Okay, and now the paper that our paper is based on is this minimum cuts in near linear time. This is the first algorithm to get complexity m and then some polylogarithmic term in n. And the rough idea is to sample edges, pack trees, and find minimum cuts that cut at most two tree edges. So what are our results? So we have a simplification of Carter's algorithm to find a smallest cut of G that two respects, which is to say it cuts at most two edges of, a spanning tree T of G. And our procedure runs in the same time complexity as Carter's. So real quick here, just give you an exact specific example so you can see what exactly it means to respect a spanning tree T. Okay, so if this in blue here is our spanning tree T, then the minimum cut that two respects T, well, it's actually just the minimum cut in the graph we found earlier because it only cuts at most two edges of T. However, if I were to change my tree so that I use this edge here, then now the minimum cut that cuts at most two edges of T changes to this cut of weight 10.5. Yeah, okay. So what else do we do? We also give a self-contained version of Carter's algorithm, and we have an implementation of our version of Carter's algorithm. All right, so since our work became available online, there's actually been two papers that also were published on arXiv dealing with this exact subroutine that we treat. and they both remove essentially a log factor in the complexity compared to Carter's original algorithm. And this first approach is going to be available at ICALP in a week or two. And the second approach, the talk is actually already available online. The complexity is slightly different. In the second one, we get m log squared n over log n plus n log to the sixth n. And actually, Carter's algorithm can run in m log cubed n over log n plus n to the log sixth n. And he just mostly just advertises the m log cubed n complexity. I guess he doesn't care too much about the log factor. Okay, so how does Carter's near linear time algorithm work? Well, the rough idea is we're going to sample edges of G. We'll pack trees in the sampled graph, and we'll sample trees from the packing, and for each sampled tree, we'll determine a smallest cut of G that cuts most two edges of T. So this first step is pretty straightforward. We're essentially, the goal, the intuition behind this step is, we're going to sample the edges uniformly at random, and the purpose of doing so is essentially going to reduce the capacity of the minimum cut while roughly keeping this same cut structure in the graph. Okay, but what about this tree packing? This is something that if you haven't seen before, you won't be familiar with. So what's a tree packing? Tree packing is a set of spanning trees, each with an assigned weight, so that the total weight of trees containing a given edge is no greater than the weight of that edge. The weight of the packing is the total weight of the trees in it. So if I just take my same graph I've been using from before, we can go ahead and compute a tree packing for it. So I can start with just some spanning tree, and I'll go ahead and make its weight the minimum weight edge of G, and this will give me as the maximum weight on the tree as I can afford. And I'll just remove that and just kind of iterate. This is not a real tree packing algorithm, but it gives you the idea of how this can be done and how the trees fit with the capacities of G. Okay, so now I have a disconnected graph G. I can't repeat this procedure anymore. If I take the union of all of the spanning trees I've packed, we see that it has total weight 8, and you can see the capacities that I've used, and there's actually some remaining capacity on just these two edges. Okay, so now there's a theorem that says that a packing of weight at least C over 2 exists, where C is the weight of the minimum cut. And there's also a lemma, this is a lemma by Carter, which says that in a packing of weight at least C over 2, each tree crosses the min cut at most twice on average. So let's let's try to unpack that lemma and see why that might be the case. So if we look at our specific example, let's go back. You see most of these trees in our packing, they're just going to cross the cut once, with the exception of this tree, which crosses the cut twice. So if you see here, the tree in the packing has weight 2. However, if you look at how much capacity of the minimum cut, remember the minimum cut is right here, that this tree uses, it actually uses 4. So the result of that is that although my tree has total weight 8, I actually saturate all the edges on the minimum cut, which is of weight 10. So what does this imply according to the lemma? Well, the basic idea is this. If I have a packing of weight at least C over 2, let's just suppose that every tree in the packing crosses the minimum cut twice. Well, that would mean that I've saturated completely the total capacity of the minimum cut. In other words, I can't have every tree, say, cross the minimum cut 3 times. And so what this basically is meaning is that in a packing of weight at least C over 2, each tree is going to have to cross the min cut at most twice average. Okay, so what does this mean? Well, this means that I can sample trees from the packing, and with constant probability, these trees are such that a smallest cut of G that cuts at most 2 edges of T is in fact a minimum cut of G. All right, so let's go ahead and focus on this fourth step. This is the main focus of our paper, and it also is the complicated part of Carter's algorithm. Okay, let's first start with a one respect algorithm, which is that giving a spanning tree T of a graph G, we want to find the smallest cut of G that cuts 1 edge of T. So we've got this graph G over here, which looks very much like a spanning tree with extra edges, which is really, or sorry, looks like a rooted tree with extra edges, which is pretty much what I was going for. And let's go ahead and call these extra edges the non-tree edges, and the edges of T we'll call tree edges. Okay, so the first question is, when is a non-tree edge UV cut? Well, a non-tree edge UV is going to be cut if and only if the cut in G cuts an edge on the UV path in T. You can kind of see this over here. I've got this UV path, and the separation, the vertex separation resulting from cutting this edge of T is such that all these edges are, or sorry, all these nodes are on one side of the cut, all these vertices are on the other. Clearly, if I have one cut edge on the UV path, then U and V are going to be on opposite sides of the cut, which implies this non-tree edge UV is going to be cut. Okay, so now the question is, how do I compute the size of all these n-1 possible cuts that cut just one edge of T? Well, here's kind of a pretty straightforward idea. So what if we just iterate an edge E through T, keeping track of the non-tree edges that cross a cut at E? So I can go ahead and just try this on our example here. I start off with this cut. There's just one non-tree edge that crosses the cut. I add this other non-tree edge, and I finally add the third one. It goes like this. These things fall off the cut, and so on and so forth. So that was actually quite easy to do when I iterated this edge E through a path. However, I need to determine all the cuts for the entire tree. So the question is there an ordering of the edges of T, or really, sorry, is there an ordering of the edges of E that I'm selecting that results in non-tree edges transitioning on and off the current cut a small number of times? So with the path, the non-tree edges just transitioned on and off at most once. But how can I? Is there a way to ensure this when I actually try to do it for the whole tree? And this is kind of the chief question that separates our work from Carter's. We're trying to take kind of this very natural, obvious, straightforward algorithm for computing these one respecting cuts at the moment, but there'll be two respecting soon. Whereas Carter's approach is a little bit more brute force. He's doing a dynamic program which does a lot of counting, and it gets a little messy. Okay, so we are going to try to leverage the heavy-light decomposition. So what is a heavy-light decomposition? The goal is to split T into some root-to-leaf paths, and we'll continue the path to the child with the most descendants. So intuitively, these paths seem to work out good, and heavy-light decomposition is a good way to break a tree into paths. Okay, so what does the heavy-light decomposition give us? Well, it implies that any root-to-leaf path requires at most O log n color changes. So why is this? Well, if I go, say I'm going down here and I transition from this blue to green, well, that implies that in this subtree, it is not any larger. There must be another subtree, at least of the same size or larger, that was a child of a parent. And for every such color change, you can say, you can make this claim, sorry, you can make this statement. And so clearly I can only do this log n times before I run out of nodes of T. And so any root-to-leaf path requires at most log n color changes. All right, so let's go ahead and just describe the one respect algorithm. So we'll iterate this edge E in heavy light decomposition order. Then we'll keep track of the non-tree edges UV that cross a cut at E, just like our first attempt. What is this going to imply? Well, a non-tree edge UV is going to transition on or off the current cut, log n times. Why is this? Well, if we look at a non-tree edge UV, there are in most log n colors on this UV path in T. And now the color changes will correspond directly with when the non-tree edge falls on and off the path. As you recall, when I'm on a path, there's just a constant number of updates per non-tree edge. So let's go ahead and just, well, we'll see how it works in just a little bit, but this is going to imply that our complexity will be m log n because, yeah, that makes sense. All right, so let's go ahead and just illustrate this algorithm. So I start here cutting the first orange edge, and all the non-tree edges are crossing the cut. They're on the cut. I make my first transition. These two edges fall off of the cut, and that's because they have this transition on their respective paths from orange to cyan and from orange to purple. And we can just keep going. See that the one that has orange is still on the path. At the endpoints, edges can fall on or off the path. Again, we keep going. This change is, again, this orange to purple change. And while I'm doing this, I'm keeping track of the minimum cuts, and I've already found a minimum cut of 1, which is clearly minimal. This is, again, due to the change from orange to cyan. And we're going now to blue, which is a color change for all of the non-tree edges. And again, this going from blue to green means this guy's going to fall off. Oh, I'm sorry, this guy falls off as well. We'll just keep going here, and eventually, yeah, we determine the minimum cut as 1. Okay, so let's go ahead and now try to take this algorithm and apply it to two respecting cuts. So for two respecting cuts, we want to, given a spanning tree T of a graph G, we want to find the smallest cut of G that cuts 2 edges of T. So we can ask again, now when 2 edges of T are cut, when is a non-tree edge UV cross the cut? Well, it's pretty straightforward. A non-tree edge UV is cut if and only if the cut in G cuts exactly 1 edge on the UV path in T. So you see here, I've got UV, I've got this path, and it's pretty clear. If I have, however many cuts I have on this path, each time I cross the cut, I'm going to the other side of the cut. So as long as the parity, if the parity of the number of cuts is odd, then U and V are going to be on different components. However, if it's even, then U and V are on the same side of the cut, in which case the non-tree edge UV will not be cut. Okay, so how can we leverage our one respect strategy for cuts that cut 2 edges of T? In particular, we cannot spend omega n squared time checking all of these cuts. Well, we're going to leverage this fancy data structure called a top tree. And top tree supports, for our application, we'll need these 3 operations, which is path add a weight W to all edges on the UV path, non-path add weight W to all edges not on the UV path, and then query minimum, which is to return the minimum weight edge in T. So here I've stolen from Wikipedia this, it's a good picture and a bad picture at the same time, but you can see here the top tree is kind of essentially a segment tree on an unrooted tree, if you're familiar with what segment trees are. And it's actually, this decomposition that it's doing is going to imply that it can do all operations in log n time. All right, so how can we leverage this for a 2 respecting algorithm? All right, so we're going to call, let's go ahead and call the 2 tree edges that we cut E and F. If we fix E, we can determine which F result in non-tree edge UV crossing the cut. In particular, if E is on the UV path, then any F off the UV path is going to result in UV being cut. Similarly, if edge E is off the UV path, then any F on the UV path will cut UV. Well, this is pretty nice then, because if you look at these updates that change, updates that are required, they are exactly our path add and non-path add operations. Or at least they can be supported by these path add and non-path add operations. So why don't we try to use this top tree to find the best F according to any particular E. All right, so here's where our 2 respect algorithm is going to be. We will iterate this fixed tree edge E in heavy light decomposition order. We will then keep track of the cost of cutting any other edge F in the top tree, and after E is moved and the top tree is updated, we'll query for the best F. And similarly to before, this is going to imply, now it's going to be m log squared n, and that's because for each of these non-tree edges, they will fall on and off the cut, the single edge cut induced by E log n times. We showed that in the one respect algorithm. And each of those times results from, sorry, is caused from E either falling on or off the UV path. And that's exactly when I need to do these updates. Now when I do an update, instead of it taking constant time, I'm just going to do a constant number of operations in the top tree, and so it's going to take log n time. Therefore, I get this complexity m log squared n. All right, so let's go ahead and just try to illustrate this on some small examples. We'll just do a few iterations. So let's say, so I start with this fixed edge E, and I have now depicted, oh, I forgot to mention, the reason I am using an unweighted tree in all these algorithms, sorry, an unweighted graph. However, everything works for a weighted graph. I just did this to make things cleaner. All right, let's go back to this. Okay, so I have this tree edge E, and we can see that initially E is on the UV path for all of my non-tree edges. So what does that mean? Well, it means actually that the smallest cut I can do is going to be this, well, it's this tiny little single vertex cut. But it also kind of shows you, if I looked at making my cut F to be something like one of these kind of leaf trees, so to speak, I get these large values, and that's because it'll result in exactly one edge being on the UV path for all these non-tree edges, and then the other edge F is just somewhere in one of these trees. Okay, so let's go ahead and just iterate this for a few times. We'll see a couple edges, non-tree edges, fall off the path. The different values for F are updated. There's no more weight 5 cut, which implies, yeah, there's no way to cut all 3 non-tree edges if I cut this edge as one of the 2 that I cut. Again, we're still getting these tiny 2 edge cuts, and this has shown that our minimum cut that cuts 2 edges is indeed 2. But okay, so there's something interesting that happens in this next iteration, and we can very clearly see the result of this non-tree edge transitioning so that the edge E is first on the UV path and then off the UV path. So we can see as I transition, all of these edges on the UV path, they get their weight increased by 1, and similarly all the edges F off of the UV path get their weights decreased by 1. And that's because when I'm now off the path, if I cut something on the path, it's going to result in this non-tree edge getting cut. And now similarly, I can now cut something else on off the UV path without cutting this edge. There's something else you can see from this particular point, which is that if I'm cutting any of these leaf trees, it's now a very cheap cut. But if I cut, say, here, I'll cut this tree edge. If I cut here, then I add this tree edge to the cut. If I cut here, then I add this, or sorry, I said tree edge, I meant non-tree edge. Okay, so I keep doing this. I didn't want to make a ton of figures, can't spend a ton of time on this in my talk, so we're just going to skip to more interesting points. The second to last iteration, there's actually no cut of weight 2, which implies I'm going to need to cut at least one non-tree edge. Yeah. And then finally we get, in our last iteration, the first kind of non-trivial cut, which is that if I want the smallest cut, I'll cut this, E, and then I'll cut something over here, one of these 3, and that'll result in a cut of weight 2. And that's so that this non-tree edge isn't cut. Okay, so that concludes the 2respect algorithm. Essentially concludes the talk. Just real quick, I'll mention that we have this implementation available at the following address. And it takes about 200 lines of code to program the 2respect algorithm. And you can see this near linear time complexity of our implementation. Our implementation actually adds an extra log factor. Instead of using a top tree, we just use a binary search tree with a heavy light decomposition again, which is log squared n instead of log n. And yeah, as far as I know, I think our implementation is actually the first minimum cut implementation that achieves near linear time complexity and is theoretically rigorous. And that concludes the talk. Thank you so much.